Calculating molar heat capacity. Before we get started on this, don't get scared by molar heat capacity, specific heat capacity, heat capacity. Basically, the relationship between heat capacity and heat is that the heat capacity is going to be multiplied by the change in temperature, delta T. And then if your heat capacity is the specific or molar heat capacity, that is going to be the amount of heat per either gram or per mole of material, whereas just heat capacity is for the whole object, okay? So essentially, the three equations you've probably come across that involve Q, delta T, and heat capacity are essentially the same equation, okay? You've got Q times the heat capacity, delta T. The units of the heat capacity are just going to be in joules per degree Celsius or joules per Kelvin, same thing, okay? And delta T is just going to be in Kelvin or degrees Celsius is equivalent, right? The size of a delta T, as in the difference in temperatures, doesn't matter what absolute scale they're on. All that matters is the magnitude of the size of a degree. So joules per degree Celsius and joules per degree Kelvin, you don't say degrees Kelvin, you just say degrees Celsius. It's the same, okay? So you don't have to worry about converting that. So you can see from dimensional analysis, that is going to give you Q in joules, because the per Kelvin, the Kelvin are going to cancel out. Okay, in terms of specific heat capacity, it's the same equation, but specific heat capacity is C subscript S, and the units of that are going to be joules per gram per Kelvin. Okay, so notice if you just times that by Kelvin for the delta T, your units of Q are going to come out as in joules per gram, and we don't want that. So that is why for specific heat capacity, you multiply by the mass in grams, because then grams times by the specific heat capacity in joules per gram per Kelvin times Kelvin is going to give you your value for Q in joules. And then finally, the molar heat capacity. So Q equals the molar heat capacity. I use C subscript M. I've also seen C subscript N or C subscript P. There's a few variations, okay? The molar heat capacity is given in units of joules per mole Kelvin, okay? So multiply that by Kelvin, and your Q would come out in joules per mole. So therefore, you have to multiply by the number of moles of stuff in order to get your value for Q in joules. Okay, so same equation for each of those. Now, we're asked to calculate the molar heat capacity. So that is going to be this one. Number one way these kind of questions go wrong is we've been given a mass in grams, and if you just stick that straight into your equation for molar heat capacity, you're going to be in trouble, right? Because we have to convert mass in grams to moles. And in fact, we have to convert mass in milligrams to moles. How rude. So we've got to go from milligrams, this is my plan, to grams to moles. And then I can substitute in my expression for the molar heat capacity, and I've got to rearrange that. So my molar heat capacity is going to be given by Q divided by my number of moles, N, times my difference in temperature, delta T. So just like we were doing with our change in volume, our delta volume being the final volume minus initial volume, it's the same for our difference in temperature. Delta T is always defined as the final temperature minus the initial temperature. All right, do we have all the things we need? I think we probably do. All right, one more thing, the molar mass of C2H2Cl2. Quickly calculate that up. So 2 times 12.011-ish plus 2 times 1.0079 plus 2 times 35.45. Depending on what periodic table you use. I'll use the ALEKS one. Have the right number of sig figs. So 1 mole of that weighs exactly 96.92688 grams. So there is our molar mass written in terms of equivalency. And milli, the milli prefix is 1 milligram is 10 to the power of minus 3 grams. So now we really do have everything we need, okay? So 508.0 milligrams, convert that to grams. So milligrams goes on the bottom and grams goes on the top. So 1 milligram is 10 to the power of minus 3 grams. Sweet. So right now we convert milligrams to grams. Then we have to convert grams to moles. So that 96.92688 grams goes on the bottom, and 1 mole of C2H2Cl2 goes on the top. And dimensional analysis should tell me that I've calculated number of moles. So I guess we should, go ahead and do that or something. So just making sure that milligrams is cancelling Oh, that's not the line I meant to draw. And the grams is cancelling too, so we end up in units of meals. All right, so 508. Hello, calculator, come on. 508 times 10 to the minus 3 divided by 96.92688 gives me 0.00524106 moles. I'm just going to keep loads of sig figs for now. I can round at the end. So then I'm going to solve for my molar heat capacity and just make sure my units should come out in joules per mole per Kelvin, okay? So I've got my Q on top, which was 7.54 joules. Of course, if that had been given in kilojoules or something, I would have to convert that, right? Then my number of moles was 0.00524,106 moles times delta T, final minus initial. I'm just going to go straight ahead and do it, right? So 19.1 minus 6.8. Okay, you don't have to worry about like converting each of those into Kelvin and then doing the subtraction, because if I add 273.15 to 19.1 and 273.15 to 6.8 and then subtract one from the other, gonna get the same number for the difference, right? So it doesn't matter, right? Is what I'm trying to tell you. Okay, so just, you know, in terms of saving times and exams and whatnot, the one thing you do have to be careful with is when you have like negative degrees Celsius, and if you're just careful with parentheses and sign conventions, you still should get like the magnitude of the difference between those two is like 12.3 degrees, right? So just make sure that it doesn't go a bit squiffy when you have negative degrees Celsius and you understand what that negative part of the temperature, because I can't even talk today, that negative part of the temperature scale actually means. I've been naughty because I didn't put my units in. So you should see my units come out as joules per mole per Kelvin. So I'm not very good at using my calculator. 7.54 divided by 0.06446. I think I put the right number of zeros in. I was trying to remember the number that came on the bottom. 1 miserably. 7.54 divided by open parentheses 0.00524101. Oh my gosh, I should have pressed the back button. Sorry, this is probably very boring for you. 7.54 divided by 0.00. Watch an old person try and use a phone calculator. And it was 12.3, the difference between those two. Yeah. I think I did the wrong. When I tried to memorize the number that I divided for, I think I did the wrong number of decimal places. 11.696, I think, is correct. And that'll be, of course, in joules per mole per Kelvin. Let me just double check that I have used the calculator correctly. If you get two different numbers, that's always smart, right? 0.00524 times 12.3. Is that the right order? Now I get 116. Oh my god, I really cannot use this calculator. If I'm going to get a different number every time, I just give up. 7.54 divided by 0.005. Maybe I should just like press the buttons slower, but what's the fun in that? Okay, definitive answer 116. Okay, and how many sig figs? 3 sig figs, so 117 joules per mole per Kelvin. Okay. And I just double checked the answer for that because I was like, I really did screw up using my phone calculator. That is the correct answer. All right, so that's all we need to do for that one. Just be really careful if you're being asked for molar heat capacity, you have to multiply it by the number of moles of the thing, and you were only given the mass in grams. So you've always got to remember how to convert between mass and moles.